I'm stuck between saying good morning and good afternoon. It's like 11:59. So I think what we're going to do, I'm trying to get multiple windows up here. We're going to try to communicate in the chat. So I have a chat window up here. If anyone needs the document we're going to work on, I can share a link to that in the chat. You might have to copy and paste. I don't think the link will be active. You'll have to like copy and paste. Hey, Nick. If you need, like if you're gonna get some extra credit for this, you should type your name in the chat so that we can kind of see that you are here. We'll give people a few minutes to get in. We have our new student trustee is here. Welcome, Taylor. Okay, I've got multiple windows up. I don't know how this is going to work. You should be seeing the practice document here in front of you. If you need a copy of it, I might keep pasting the link periodically because I think when you join, you can't see the previous chat. So I'm going to I'll paste it periodically. You have to copy and paste that. It's just a PDF. So here is how these usually work, and it's going to be a little bit different right now. Oh, I have to make sure I'm recording. Yep, I'm recording. Requesting an access code. Yeah, you need to be logged into your student Gmail account. I don't think, because it's in my, whoa, what's happening? I don't think that I can share it with everyone. Let me see here. Hold on, I have like too many windows open. My browser is like giving me issues because it's in my ECC Google account, and I know sometimes it's restricted. So let me see. Let's see. Okay. Anyone with the link? There we go. All right. Anyone with the link can view. Cool. All right. You shouldn't need to log in now. So try again, Nick. See if that works. You should be able to log in. Oh, we have someone waiting to come in. Okay. So this is like a really, really long document. If we were to do every single thing on here together, this would take like 6 hours. So my goal is for you to kind of hopefully you've been emailed it already by your instructor, or you can look at it now and we can just take requests. That's usually how these work. Fair warning, I know we have Mth102 and Mth120 people were invited, and the stuff at the end, where does it start? Page 10. There's some additional Mth120 stuff, and so if you're in Mth102, this is not content you would have covered, and so you may have to be patient while if somebody asks about that. So, I mean, I could start at the beginning and just go through, but I think it's way more efficient if you kind of peruse and then just type in the chat which problems you would like. So I'm going to give you a couple minutes to do that. And after we get a few requests in the chat, we will dive right in. And again, if you need this for extra credit, go ahead. We're going to save the chat, so maybe just type your name in the chat so we can have a record of you being here. So as soon as you see something that you'd like to do, feel free to go ahead and type a request. All right, so Jessica is having trouble finding the lower and upper bound. And okay, so you use Statcrunch. This is one important caveat as well. So one of the challenges with this course is with statistics in general, actually, is there a variety of tools that you can use. And not everyone is going to have the same, not every instructor is going to use the same. So whether you use the calculator or Statcrunch, we might need to go through both. So Jessica, I'm glad you used Statcrunch because that's what I used to. So I'm super familiar with that. 10.2, gosh, I have to remember that. Are we talking about proportions or means? Do you remember if that's about proportions or means? I actually teach 120 this semester, so the section numbers are different. Do you know, is it about percents or about averages? Let's see if we can find that stuff here. Jessica, I want to make sure I'm doing the right one. Averages. Sure, well, we can do both. So let me paste in the chat again the link. We had a few people join us. So you'll have to copy and paste this URL. So what we're looking at right now is confidence intervals. So we're going to do, let's do mean and let's do proportion. Let's do both. So I'm looking at number 11 on the document that's linked. And then we'll find a mean. Yeah, mean is number 12. So they're right next to each other here, number 11 and number 12. So first of all, for number 11, let me actually save this file as like key or solutions or something. So first of all, to find a point estimate for the proportions of gasoline stations with at least one leaking underground tank. Oh boy, 18 out of 107. That doesn't sound good. You're very welcome, Michael. So let's say p hat, that's our sample proportion, that's our point estimate. That would be 18 out of 107, which is approximately, got my handy dandy calculator here. I think it's easier to do on my phone. 18 out of 107, so about 0.168. That's our point estimate. And then Jessica's question was about the confidence interval. And we're going to show this in Statcrunch. We can talk about this in the calculator if you would like, but I do have a Statcrunch window up here. 18 out of 107. We got to remember that. Okay, Statcrunch. Here we go. So this is under stat, and this is proportion stats. Stats, proportion stats, one sample with summary. It feels like we have data, the 18 out of 107, but that's actually just a summary. So again, stat, proportion stats, one sample with summary. And it's 18 number of successes out of observations, 107. And we're doing a confidence interval. And let's make sure we're doing the right confidence interval, 95%, okay? So yeah, 95%. It compute, and there's a lot of good stuff here. Here is the lower limit and upper limit. And I usually round to like tenths of a percent. So I would say like 9.7% to 23.9%. So 9.7% to 23.9%. Construct a 95% confidence interval for the proportion of gasoline stations. So there it is. A little insert here. Sometimes we're asked for the margin of error instead. I often ask that. And so the way you can find the margin of error, the thing to remember about confidence intervals for the proportion is the point, this is 0.618, right? That's 16.8%. That's in the middle. And then it's plus or minus the margin of error. So what you could do is you could take the 23.9% and subtract 16.8%. And I should be able to do that in my head, but I cannot. 7.1%. Maybe I can't do it in my head. 7.1%. So if that was asked, it wasn't asked here, but that's how you would do that. So that's how to find the lower and upper limit in Statcrunch for a proportion confidence interval. Okay, and let's look at number 12. In a simple random sample of 87 young adults, the average time per day spent asleep was 7.06 hours. With a standard deviation of 1.11 hours, find a point estimate for the mean number of hours a young adult spends sleeping. Well, that's given to us here. That's actually X bar, and that's 7.06 hours. So that is our point estimate. And we'll go back to our Statcrunch window. Boy, this one, I usually use data. So this one would be T-stats, one sample with summary. So T-stats, we could spend a lot of time talking about Z-stats versus T-stats, but we have sample data here. So because this is data from a sample, we want T-stats. T-stats, one sample with summary. And then we'll type in the information. 7.06 is the mean, 7.06. 7.06. Sample standard deviation, was it 1.11? 1.11. This is all from a simple random sample. That's how I know that's the sample standard deviation. And then a sample size of 87. Let me just do a little side note here. See, there's always a few students who understandably get confused between Z-stat and T-stat. And here's what's confusing. If I do Z-stat, one sample with summary, it has the same stuff, but you'll notice it's just very subtle difference. You see the difference? Sample mean, oh, okay, 7.06, and then, whoops. And then you see the standard deviation and you think, oh, it gave me the standard, it says right there, standard deviation of 1.11. So the problem is, see for T it said sample standard deviation. And if you read this sentence very carefully, in a simple random sample of 87 young adults, the average time spent was this with the standard deviation of this. See, this 1.11 is only from the sample, So it actually, the intervals probably won't be very different, but we should be doing a T interval here. And I always tell my students, most of the time you have sample data, so when in doubt, do a T. Confidence interval, being a little sneaky on us here, 99% this time. So we got to change this to 0.99 and hit compute. And just like the other one, gives you a lower and upper limit. We should round to the same what the sample mean was. So I think it was 2 digits. So we'll say 6.75 to 7.37. 6.75 to 7.37 hours. And again, if we were asked, we could do the margin of error, and that would be just taking the difference, 7.37 minus 7.06, 0.31 hours. It wasn't asked, but that's often a question. Okay. So Jessica, you were asking about finding the lower and upper limit. We did a confidence interval for proportion. We did a confidence interval for the mean. So how does that feel? Any thoughts about that? Any further questions? All right, for those, sample size. Okay, so Vicky, yeah, I was focusing on the confidence interval because that's what was asked. But we can certainly do the sample size needed questions here too. Let me paste The link again, if anyone joined late, we're doing some examples, and this is all going to be entirely by request. I mean, if we don't have any requests, I can start from the beginning. So feel free to type in the chat at any point what problems from the review you would like to do. So we have a request from an instructor to find the sample size necessary. So what these are, you have to kind of forget the earlier part of the problem. So this is what this is saying is, suppose you're a researcher and you want to do this study, and you want to find a confidence interval, and you want your confidence interval to have a specific margin of error. So what we're going to do is we're going to use this formula, which is a little confusing. So the formula here, the P, let me kind of type all this out in words. So this would be the point estimate. Now, sometimes this can be a previous point estimate. Sometimes this can be, if you don't have any guess, you just put 1/2 there. Q is 1 minus the point estimate. The Z alpha over 2, we'll talk about that notation. You should hopefully know what that means. So, but we can talk about that. And then that E is the margin of error, the actual margin of error that you want. Okay, so let's try that for this one. The instructions say here to use the point estimate that we have from initially here, which is honestly a little weird, because what we're saying, it's kind of weird because it's, we have this survey that was done and we got the point estimate from the survey, and now it's saying use that point estimate to see what you would do if you wanted to get a margin of error of 0.03. So I think basically what this is saying is, this is a pretty wide margin of error. So there's a lot of uncertainty there. We need more data. How can we get a narrower interval? We're going to use the 16.8% as our guess. How can we get a narrower interval that only has a margin of error of 0.03? So the way this works is we put our original guess, which was 0.168, and then 1 minus 0.168. And then we have to do this whole Z thing, got to figure that out. The denominator is 0.03, that's our margin of error, and we just need to figure out the Z. So here's the key for the Z. When we want a 95% confidence interval, this means that that alpha is the remainder, kind of the leftover, 0.05. So that means we need a Z sub 0.05 over 2, so was it 0.25. So hopefully your notation, hopefully you're comfortable with that notation. Let me jump over, we need that Z 0.0125. I'm gonna jump over to Statcrunch. The way you find those, it's a normal calculator, StatCalc normal. And we need 0 and 1 because it is a Z. That 0.025 is the area to the right. So I'm going to make this to be greater than, and I'm not putting 0.025 as the X value. The 0.025 is the area, 0.025. So Z 0.025 is the Z value with 0.025 to the right. And that's this 1.96. If you've been doing a lot of these problems this way, you will recognize the 1.96. It's a common one. See your question there, Nicolas. Well, that's a good one too about some of the hypothesis tests. So we'll do those next. That's a good one. All right, so typing everything again, I can cheat and just copy paste. We have 1.96. I wonder if I can like copy and paste this like in Google. Will it do it all for me? Yes. Awesome. 500. Now you always, here's the thing, we're looking for a margin of error. We want our margin of error to be 3% or less. So we need our sample size to be at least that number. So you always round up. You always round up. So even though here we would round up anyway, we would always round up here. And so we're going to say 597. What that means is, boy, that's a big difference. We had 107 gas stations, and we got a margin of error of 7.1%. If we want to get a margin of error of 3%, we would need almost 600 gas stations. Getting that margin of error down is easier said than done. So that's that one. And then there's a similar one here for means. Ooh, this formula is a little funky. Oh, it just looks weird. Okay, so what this is, let me just do this in words. It's again the z alpha over 2. And then you multiply by a previous standard deviation. You have to have that somehow. Somehow you have that. And then you divide by the margin of error. And you square that. So this one, let's see, what margin of error? We want a 5. Ooh, that doesn't make sense. Uh-oh. Uh-oh. Can't have a 5%. It's not a, uh-oh. This is not good. This is the confidence interval for a mean, not a percent. It doesn't make sense to have a 5% margin of error. I need to make a note to myself. Fix 12C. Fix 12C. So let's give ourselves, let's say we want to have, so this was our margin of error 0.31. We want to be smaller. So let's say we want it to be 0.2. All right, that's what we want to be our margin of error. Okay, so we're going to say 0.2 here. We have our standard deviation. We're going to use the one from the sample. And then we're going to square that. And I'm going to need to figure out a z. And unfortunately, it's not the same one. I don't know if you can tell why it's not the same one, but it's a different confidence level. It's a different confidence level. So 99% means that the alpha equals 0.01. So we need to find z sub 0.005. Half of that, half of that. So that's Statcrunch again. And same one here, and we just put 0.005 over here. Compute. That's 2.58, call it, 2.58. Oh, nope. It's the z that was 2.58, 2.58. All right, and we're going to use our handy dandy calculator called Google. Paste 205. We need 205. Oh no, 206. I didn't follow my advice. Always round up here because you want to get that margin of error or smaller. And so if you had more than that, your margin of error, or sorry, if you had less than that, your margin of error might be a little bit wider. So that would be, we'd want about 206 young adults in our next sample if we wanted to lower the margin of error to 2%. Okay, so any questions about part C on 11 or 12? Okay, so Nicolas was asking about the hypothesis test. Do you remember, you said 10.3, but is that a question on here? And they're not labeled 10.3 on here. So
no, it's not. It's a homework assignment, 10.3, question 3.
Looking for a hypothesis test.
Yeah, it says identify the critical value, select the correct choice below, and fill in the answer.
Confidence intervals. Here we go, hypothesis test. So these two? Yeah, 9 and 10. So Nicolas, you had asked about hypothesis test using the classical approach, find the critical value, test the hypothesis. So again, is that a mean or a proportion? Probably proportion. I mean, probably a mean. I'm guessing.
Give me 1 second, I'll take a look. It's the question just asks, use the classical approach at the alpha.
Thank you. Thanks for your help. I need to have that book in front of me because the sections are different from 120. So let's do 9 and 10 because these are the more recent ones, kind of at the end of your semester, and so they're probably less familiar to you. Okay, for the past several years, the mean number of people in a household has been declining. The social scientists believe that in a certain large city, the mean number of people per household is less than 2.5. So this might be like historically it's 2.5, and so now we think it's less. So she takes a simple random sample of 150 households in the city with the result of a mean of 2.3 and a standard deviation of 1.5. We're going to test at the 0.05 level of significance. Now this one says using the p-value method. I can do that, but Nicolas specifically asked about the critical value method, so we'll do both methods. Okay. So the requirements for a mean is you either have to have either a normally distributed variable, and we don't know that here because our variable is number of people per household. We don't have any information about whether that's normally distributed. So we're kind of out of luck with that one. Or B, sample size of roughly at least 30. It's kind of vague. That's why statistics, we kind of wave our hands at things with no outliers. So we don't really have a lot of information here. We do have n equals, lowercase n, sample size equals 150. So it's safe to say the requirements are met. We don't know if there is like, say, a household size of like 27 or so, I don't know, let's just make it some ridiculously large number. But we don't know that. So we have to kind of work under the assumption. The sample size is really large here, so that kind of buffers for any outliers. Okay, so the hypothesis test. When I teach this, I have 6 steps here that I do. So I like to specify the null and alternative hypothesis and state the alpha level, calculate the test statistic, and here's where we're going to do either the critical value or the p-value. So we'll do both methods here. And then we'll make our decision, reject the null hypothesis or do not reject the null hypothesis. And then we'll make our final conclusion. And I do these 6 steps for every single hypothesis test. So what is going to be required for you, I don't know, but I actually require my students to do all of these tests. So our null hypothesis in this case is the old mean, that it hasn't changed, and so it would be that the mean is 2.5 people per household. And then it looks like the scientists believe that the mean number of people per household is less than 2.5. Less than 2.5. This would be more like a sociologist or something, by the way, anyway. Wouldn't be a scientist per se. So mean is less than 2.5 people per, people per household. Okay, alpha is 0.05. I don't know if you want to type this, Nicolas. Did you say you're using calculator? Are you using calculator, Statcrunch? No. There's so many ways to do these. Are you using formulas? Okay. Okay, but that's fine. I don't care. You just need to tell me what you want to know how to do. So do you want to do it on the calculator then?
Whatever is easier. If it's easier to do it on Stat, then that'll be Statcrunch will probably be better.
Are you in Vicky's class?
Yes.
We should do Statcrunch. It's way easier if you have that. But again, not everyone has that, so that's why I'm waffling. So this is just like for the means. This is a T, like the confidence interval. This is in T-stats, And this is one sample. We do not have the original data. All we have is the summary. So stat, t-stats, one sample with summary. Okay, and then we write in all our information. Sample mean of 2.3. Standard deviation is 1.5. Sample size is 150. We type in our hypothesis test. This is really why I make my students do that, so they're not just guessing here, because they have it all written down. Mu equals 2.5. Mu is less than 2.5, right? Yeah, 2.5, and we think it's smaller now. All right, and we hit compute. All right, and this one gives us a p-value. Oh, here's the t statistic, negative 1.63. So t equals negative 1.63. Critical value is what Nicolas was asking about, so we'll get to that. P-value was 0.0, was it 523? 0.523. Okay, that's mean that's so close. Oh, that's like the worst. If you're an actual statistician and you get a p-value like that, you'll look, no. Oh, so close. Critical value here, we need to look at the t distribution, and we need to find the t value that on the left, this is my left, maybe you're right, I don't know if it's reversing the video, but that's on the left that has 0.05 area to the left of it. So we need to go on the normal calculator, sorry, t calculator. And ooh, degrees of freedom. This is 1 less than our sample size. That's 149. And we're gonna do, we want less than, and we want 0.05 because that is our alpha level here. That's our level of significance, 0.05. So what you're doing is you're finding like a tail, and whether it's left or right depends on your alternative hypothesis. So ours is left, we go left. If it's split, then you split it in half. If it's a not equal to. So here's the value, negative 1 point, we'll call it negative 1.655, negative 1.66. And you can see here the negative 1.63 is like, oh, so close. Negative 1.63 is right here. So close, but not in the red region. Not in the red region. Very close. Oh, again, that's just mean. That like hurts my statistician soul to be so close. So the p-value is just higher than alpha. The critical value is below. The test statistic is not in the rejection region, so we do not reject the null hypothesis, but we feel sad about it. So the conclusion, nope, there's not enough evidence at the 0.05 level of significance to support the researchers' claim that the household, the mean number of people per household is less than 2.5. So close, so close. But that's it, it's an up or down vote. You can't say, well, it's kind of, it's like, nope, it's a cutoff value. Either there is or there is not. This is one of the dangers, by the way, like if you had 20 people do this same study, one of them might just randomly be low, or maybe this one randomly was high and all the rest of them were low. So you have to be careful. This actually happens in publishing, where they'll do an experiment like 20 times, and they'll all be like, oh, so close, so close. Then they'll find the one that's low, and then they'll publish that one. Very sneaky. So what you could do if you were this researcher is you could maybe do it again and then have a sample size of like 300. You could collect more data to see, because it is close. It is kind of interesting. Like, well, it's not like there was zero. It's a little low, but maybe we could do it again and get a larger sample size. But with the data we have, nope, we do not with that. So I want to do number 10 also, but I think this was the one you were asking about, Nick. So does that, Nicolas, does this answer your question? Or did you say Nick up above in the chat? I can't remember. You did say Nick, right? Yeah. So Nick, does that answer your question? All right, excellent. Let's do number 10 too, because this is the other kind of newest topic for everybody. This is a hypothesis test about proportions. All right, so a general social survey sample, general social sampled, right? Sampled. 1,016 employed people and asked them how satisfied they were with their jobs. Of the 1,016 people sampled, 568 said they were completely satisfied or very satisfied with their jobs. We're going to test at the 0.01. Ooh, this is very, very high threshold here. We got to be really sure. Test at the 0.01 level of significance that the majority of people are completely satisfied or very satisfied. Okay, the requirements here is that n times p hat times 1 minus p hat has to be at least 10. So let's try that. We have n, 1,016 times p hat, which will be 568 out of 1,016, times 1 minus 568 over 1,016. And yes, that's really big actually. Definitely greater than 10. Okay, and then there's a second condition, and the sample size must be less than 5% of the population. This one is a little vague about, they're both kind of hard for students, first time stats students to understand why they're there. This one's a little abstract. Basically, if you get too large of a sample, you can't assume independence anymore. But anyway, it's just a requirement. So it must be less than 5% of the population. So this one, we're looking at employed people. So 1,016 is definitely less than 5% of all employed people. So yeah, good. Okay, requirements met. Done. All right, hypothesis test. I am going to copy and paste my steps from above. Now, things are going to change, of course. It's a different test. But we want the same 6 steps. So we just have to delete all our stuff here. Okay, excellent. Okay, so null hypothesis here. Oh, that's sneaky. Test at the 0.01 level of significance that the majority of people are completely satisfied or very satisfied. So majority means more than half. So the null hypothesis is that the proportion is 1/2, or 0.5, are completely or very satisfied. And we are wondering, my brain's on statistics, satisfied. We are wondering if the majority, so we're wondering if it's more than half, are completely or very satisfied. Okay. So one of the challenges here is kind of figuring out what the null and alternative hypotheses are. Okay, alpha is given to us here, 0.01. Okay, we're going to go to Statcrunch again, and it's the same menu that Jessica asked about earlier for the confidence interval. It's going to be proportion stats. 568 out of 1,016. Okay, so we're going to close. Stat, proportion stats, 1 sample with summary. 568 out of 1,016. Null hypothesis, yep, p is equal to 0.5, and then we are wondering if it's more than that, if more than half. Okay. Compute, all right, so here's a z statistic, 3.76, very high. And then our p-value is actually less than 0.0001, very small, very small. Critical value, this is a Z now. This is a Z, so we'll do normal calculator because it's a Z. And you know to do Z or T just based on the type of test it is. So means are T's, and then proportions are Z's. So do Z, and we did we did right-tailed, we did greater than. So we're gonna do greater than, and we want 0.01 to be the area, 0.01. So 2.3, we'll call it 2.33. All right. So what do you think? Should we reject? Anybody have any ideas? You can type in the chat if you want. Should we reject the null hypothesis? We have a p-value that's very, very small. And we have a test statistic that is way over here. And Nick is right. He says, yes, we should indeed, because the test statistic is in the red region here, and the p-value is less than alpha. So yes, reject the null hypothesis. And so conclusion, there is enough evidence at the 0.01 level of significance to support the claim that the majority of people are completely or very satisfied with their job. Done. All right, any questions? Yeah, kind of. So what this says, Nick is saying, doesn't the p-value show the likelihood of the event occurring? What it's saying is, if it's equally likely to be either completely satisfied or very satisfied or everything else. So if those two options are equally likely, that would be the probability of getting this result, 568 out of 1,016, which is, what is that? So that's 56%. So what it's saying is the p-value is saying, well, the probability of getting a 56% proportion, if the proportion is really 50%, is almost impossible. It's less than 0.0001. So the p-value is the probability of observing what you did if the null hypothesis was true. So if the null hypothesis was true, if the proportion was 50%, so if only half the people were completely or very satisfied, the likelihood of getting 56%, 568 out of 1,016, is basically impossible. So that's what the p-value says. It's the likelihood of what you observed happening if the null hypothesis was actually true. So the odds of our thing happening, very, very small, very unlikely that it happened randomly. So the proportion is probably greater than 1/2. That's what we concluded. Yeah. Any other questions about that one? Would anyone like to see how to do these tests or confidence intervals on the calculator? Is there anyone here who would prefer a calculator? It would only be if only do that if you need the calculator for your test. Statcrunch is better, but if your class uses the calculator, you should know how to do that. Does anyone want to see that? Right, not seeing anything. So I think now let's open it up. We had a few requests for, where did my video go? Well, there it is. A few requests for confidence intervals, and we did hypothesis testing. These are mainly 102 topics. So who has additional requests? You can see how we're not going to have time to go through the whole thing. So it's best to focus on questions you have. So are there any additional requests from that practice file? The worst part about these Zoom things is like when there's silence. Can't tell if people are like thinking or waiting for someone else or typing or I don't know. All right, I need to give you a few minutes because you do not want me to just walk from the beginning because we're not gonna have time for everything. Well, I don't know, maybe we would. There's only 12. Maybe we would, all right. You know what, let's just do it. We'll start at the beginning, we'll see how far we can get. Feel free to interrupt me at any point if you have specific requests. So I'm gonna type in here. This is one question that I actually ask my students as well to make sure they know all of the symbols. So let's do this. Statistic for the mean, that's the calculated X bar. And the parameter is mu. Let's see, variance, that's S squared for the statistic, and the parameter is sigma squared. Yeah, standard deviation would just be S, and then for variance, it would just be sigma. Proportion, we did some of these already. That's my P hat. I love that the equation editor actually calls it hat. Like the bar, it's actually called bar. The correlation coefficient is R. This looks like a P, it's actually the Greek letter rho, and you probably never saw that in your classes. So, but the correlation coefficient is one thing you did. So the difference between statistics and parameters, statistics are associated with a sample, and parameters are associated with a population. So all of these here, X bar, S, P hat, R, those are all associated with a sample. And mu, sigma, P, et cetera, those are associated with a population. Okay, so no one has said any calculator. So I'm just gonna keep using Statcrunch. So you need to stop me if you wanna see some of this stuff on the calculator. We're gonna make a table. We could probably do this one by hand. Use a class width of 30, taking 90 as the lower limit. So 90 to, oh, now you're making me do math. 90 to 1, it would be 120, so 119. Here, let's do the lower limits. We'll add 30, these will be all the lower limits. 150, 180, 210, and 240, okay. You gotta make sure your lower and upper limits don't overlap. And so if you just do the lower limits first and then go up to them, they don't have to do as much math. A bit easier. 219, 239. I do have to do the last one though, plus 29, 269. We could do this in Statcrunch, but there's only 18 of them. We can probably just add them up. Plus they're in order. So 90 up to 119, that's 6 of them. 6. 120 to 149, oh, just 1. 150 to 179, just 2, interesting. 180 to 209, 1, 2, 3. 210 to 239, 1, 2, 3, 4, and then 240 to 269, 2. All right. Oh, I am gonna need to get this into Statcrunch because we need to do a QQ plot. This is gonna be a little tedious because Statcrunch wants them in one row. So we're gonna have to copy and paste them. Which one do I want? This one. This is gonna be a little annoying here. I'm gonna paste, but then I'm gonna have to like copy, paste. It's annoying. Copy, paste. I could share this with you if you're not following along. Data, save, Mth102, 120, final exam review, save. Okay, and then, what am I trying to do? Shoot, properties. Yes, updates. Okay, I'm going to paste this in the chat, and if you want to, you can open that up in Statcrunch. Okay, so QQ plot is another plot, pretty easy. Graph, QQ plot, you just got to know where it is and then how to interpret it. So graph QQ plot, we'll do our variable, and we're going to hit compute. And what we're looking for here is linearity. We want it to be a nice straight line right along that red line. If you have a little variation from it at the end, that's okay. We want it to be right along that line because we're looking to see if our distribution is bell-shaped, and the theory behind it is the vertical axis is what our actual data are, and the horizontal axis is what they should be if it was normal, and so there should be a linear relationship between those. You can also look at a histogram to kind of give you some additional information. That does not look normally distributed. And if you look at this graph, I don't know if you can see these guys right here, these are problematic. That's not good. Even up here, like it separates from the line, but especially down here, that's not good. That is not good. That's a definite no for me. So for me, I would say no. This is pretty certain here. No. These data do not come from a normally approximately normal distribution, normal population. The QQ plot deviates from linearity too much. All right, I wrapped around to the next page here. That's kind of annoying. Need to cheat and gain some space from my table. All right, so again, what you're looking for on the QQ plot is you're looking for linearity. And that was, again, in Statcrunch, it was graph QQ plot. And so definitely not linear. All right, this is so interesting because I could really just be talking to myself right now and I would have no idea. Okay, let's look at the next one here. Oh, we're gonna have to type all this data, these data into, because we're gonna need to find the sample mean, the mode, the standard deviation, the median, and the variance. So let's look at Statcrunch and we'll type all these in. I should be able to save my file and then you can just hit refresh. We'll call this study 4, 6, 6, 7, 10, 10, 10, 12. 4, 6, 7, 10, 10, 10, 12, 8 of them. Oh, there's a 16. Okay, 16. Data, save, yep, overwriter. Okay, so if you want to, yeah, Vicky, you can do the correlation. I don't know if you ask your students to do that. I think that's a little, I don't think students really understand what they're doing with that. So if we do the QQ plot and you want the correlation on there, you can, where's my result here? QQ plot. You can add the correlation statistic. The problem is we don't really know what that means. And there are these, it's just kind of hard to interpret. Yeah, I don't know. You can do that if you want. It might even be normally distributed here. I don't have that table with me. And I don't know, I just haven't taught that. I just don't think it's a useful skill at this level. So I don't have that table with me and I can't compare it. If you have it, you can like paste the link to it if you want. So maybe it does satisfy it according to that link. So unfortunately, I don't have that in front of me. All right, so I'm gonna move on to number 3 and we can maybe come back to that one if we like. Here we're just calculating sample statistics. I think I'm gonna shrink this again. And I'm gonna do summary stats columns and do study here. And we need, let's see, we need the mean. We need the variance, there's S squared. We need, what else do we need? The standard deviation. And the mode we'll have to just pick out. What else am I missing? Oh, the median. Median. There we go. Hit compute. All right, so there we have all of the stuff that we need there. Let's enter those in here. Let me see if I can do this. All right, so X bar equals 9.9, like 9 exactly. Median equals 10. The mode, if we just look at the most common, that would be 10 as well. The variance, we're going to round, so we'll say approximately, 2 P's, approximately 13, oh no, actually it's 13.5. And then the standard deviation is the one that's really, oh, why did it capitalize that? What is happening with this formatting? I'm having typing issues. Approximately 3. Now, I usually tell my students to round to 1 more than the data. So 3.7. 3.7. All right. So Vicky has some additional information for us. So I guess we should. The problem with these is I really just don't like these examples using the critical value table. So I guess we should change our answer here. The correlation formatting issues. On the QQ plot is 0.97, which is above the critical value in table 6, 0.941. So I guess it would be reasonable to consider these data coming from an approximately normally distributed population. All right, good catch on that one, Vicky. Okay. Just trying to see if there's anything else. Okay. Let's see here. So moving on, we're actually making pretty good time. Oh, it's 12:58 already. I might need to take a break in a little bit. A national organization has 3,500 members. The members were asked whether they preferred Republican platform, Democrat platform, or neither on a particular issue. You're given the information on the member responses by gender. So there are some probability questions here. What is the probability that a randomly selected member is female? All right, easy enough. We'll take the number of females, 1,500, and divide by the total, 3,500. And let's see here. I feel like I should be able to do that in my head, but. So as a decimal, what is that? If we divide by 100, it'd be 15/35. Then divide by 5, 3/7. Or as a decimal, that is approximately 0.429. What is the probability that a randomly selected member is female? All right, what is the probability that a randomly selected member is a man and preferred neither platform? So this is going to be a probability of male and neither. So male and neither, it's right here, 300, male and neither. And so what I would do, I would not use the probability rule here for addition. We can talk about that. But I would just take the 300 and divide by 3,500. That's the number that are both male and prefer neither platform out of the total. And that would be about 0.0. 86. You could use the probability rule here. The probability of male and neither, it's actually really inefficient though. Would be probability of male plus the probability of, oh no, this is an and. It would be times the probability of neither given that they were male. Oh, this is really not a good way to do it. So the probability that you're male, or that the individual is male, would be 2,000 out of 3,500. And then the probability that they would choose neither, given that they were male, that's 300 out of 2,000. And if you calculate that, that's actually the exact same thing, 0.086. So my point is, I think when you're given a table like this, finding these probabilities is much more efficient just to look at the values in the table. The next one, what is the probability that a randomly selected member is a man or preferred the Republican platform? Okay, the probability of male or Republican. Okay, one thing we could do here is we could just take all of those and add them up. So we could take 1,300 plus 600 plus 1,900 plus 400 plus 300 and divide by 3,500. So we can just brute force, add them up. Again, from the table, not too bad. And we can just calculator. Oh, I miscalculated something because we have too many. So, oh, the 1,900 is the total. Ha, can't add the total in there. So what we want to add are these counts here. That makes more sense. I'm going to add those guys and these guys. So 1,300, 600. So we want all the people that are either male. So here's all the males. That's a 200. And then we want to also add these females that are Republicans. So that will be better. And let's see what we get there. So 0.74. Here we could do a probability rule as well. So the probability of male or Republican would be the probability of male, scroll down here a little bit, probability of male, plus the probability of Republican, but you have to remove the overlap, the probability of male and Republican. So that would be 2,000 out of 3,500. Plus the Republican is 1,900 out of 3,500. And then subtracting the and is the 1,300 out of 3,500. And if we do that, we're going to get exactly the same thing, assuming I didn't make any mistakes here. Same thing, 0.74. So again, when I have a table like this, I usually don't like to use the probability rules. When I have a table, I just like to say, well, who is this, male or Republican? And just count up the males, add any missing Republicans, and then divide by the total. All right, next one, given that a randomly selected person is female, what is the probability that she prefers the Democratic platform? So we're finding the probability of Democrat given that the individual is female. What that means is we're going to change our denominator. We're only going to look at females. So we're going to divide by 1,500. Given that the individual is female, what's the probability that they prefer the Democratic platform? It's 800. I love these realistic sampling numbers. Like somehow, miraculously, they did this random sample and every count was right on the 100. What are the odds of that? Like, if they're making up numbers, can they just make up numbers that look real? Like that, that would have been more interesting. All right, so that's letter D, and oh, we had a little page break there. Oh, that's it. I'm just rolling here, so feel free to interrupt me if you have any questions at any point. Okay, we're doing some counting here. We have 65 candidates. How many ways can the following be filled? President, vice president, secretary, treasurer, and dog catcher. Okay, so you could think of this a couple of different ways. You could count, you're like, well, there's 65 choices for the president, 64 choices for vice president, 63 choices for the secretary, 62 choices for the treasurer, and 61 choices for the dog, the all-important dog catcher. All right, so we can just multiply those together. That is a big number. Oh, sorry. We need some commas in there. That's a really big number. 991 million. So you might recognize this. This is actually the same as a permutation. So it's actually the same as 65 P5 because order matters because president, vice president sets a specific order, and then you're choosing 5 of them and they can't have any repeats. So those are the same thing. A 6-person committee is actually harder to do by directly calculating because you can't do 65, 64, et cetera, down to 60 because order doesn't matter now. So you have to divide by the number of ways to order them. It's way more efficient to use a combination, 65C6. I don't know, actually I have a combination thing on the calculator. I know there's a lot of other ways to do it too, but if we do math, I believe it's under probability. There it is, NCR. And so we can do 65C6, another big number. I can't copy and paste this one. 82,598,880. That's a lot of 6-person committees that are possible. Okay. Ooh, infections. Ooh. I want to be thinking about infections right now, but not bacteria though. So at least we're not dealing with bacteria pandemic right now. 87% of all letters received by public figures have bacteria that could cause an infection. Is that true? Gross. 52 letters will be received tomorrow. Using the binomial probability distribution, find the following. Identify your variables and write down your technology steps. Again, you can do this in the calculator. No one has said they are using the calculator, so I'm going to continue to do this in Statcrunch. I'm going to find the probability that we have exactly 40. We're supposed to identify our variables here. X is the number of letters carrying bacteria. Okay, probability X is 40. Oh, wrong one. Statcrunch. We have a binomial calculator. Binomial calculator. We have N is, was it 87 letters? Oh, shoot, sorry. No, 52 letters. 52 letters. Probability of one carrying bacteria was 0.87. We're trying to find the probability of having exactly 40. So we'll call it 0.0183. All right, now we're going to find the probability of getting at least 40. So that I need to use my equation editor here. That's greater than or equal to 40. Okay, so we're going to do, that's all we're going to do is just change the X, change the inequality sign. So 0.986, about 0.9861. Find the probability that less than 40, well, I mean, we can just change that inequality, or we could do 1 minus the previous one, but we can change it to less than, it's easy enough, 0.0139. How many letters do you expect to carry bacteria? So for binomial distribution, the mean is n times p. So that's 52 times 0.87. So we would expect about 45.24, something like that. Standard deviation, this one is not used very often here, but sigma equals square root n times p times 1 minus p. So that's the square root of n is 52, p is 0.87, and then 1 minus 0.87 will be 0.13. I wonder if Google can take this. I'm just going to copy paste. We shall see. It worked. Call it 2.43. All right, and that is the binomial distribution. Ooh, I need to sketch. Well, I have a tablet, but that's like the other monitor. So you might, I don't know. I'm gonna just draw them on here and then we had some new people. I don't know how long they were waiting. Oh no, sorry, I haven't not been monitoring it. Welcome, new people.
There we go.
Where did the link go? We are working on some practice documents. They are in this file. So I'm going to see if I can draw these quick with my pen on my tablet, and then I'll bring it back over to the other monitor. So approximately normal, it would be bell-shaped, skewed left. Oh, nope, wrong way. And skewed right. All right, so something like that. There we go. Very sloppy, approximately normal. Skewed left, big left tail, skewed right, big right tail. All right, we are rolling along here. Number 8, we have weight and fuel economy, construct a scatter plot. Oh no, Statcrunch is not gonna like these in this order. That is unfortunate. I feel like we are going to need to copy or like just type them all in. Ugh. So weight, 8, 24.5, 27, 14.5, 28.5, 12.75, and 21.25. And then we have miles per gallon. Is 7.69, 4.97, 4.56, 6.49, 4.34, 6.24, and 4.45. I'm going to save this data again. Oops, not export. And I'll paste that in the chat again. And if you would like to follow along in Statcrunch, you should be able to copy and paste that and log in and do this. Let's do everything we need to do here. So we are asked to do a scatter plot and then do some calculations here. So scatter plot is a graph scatter plot. We'll do weight predicting miles per gallon. So weight as X miles per gallon as Y. We always want a title. So I'm going to go down to the title. Miles per gallon versus weight of trucks. Fancy title. There we go. No surprise, bigger trucks, lower mile per gallon. We'll copy that. And we'll paste that in here. Oop, that did not work. There you go. All right, expectations for R based on the graph. Definitely negative. Negative fairly strong. They seem to be pretty in line, maybe negative 0.8. I don't know. All right, so let's do technology. Let's actually calculate R and R squared. So that is under regression, simple linear. X is weight, Y is miles per gallon, and we'll hit compute. And it gives us R, oh, it's stronger than I thought, negative 0.94. So a very strong negative correlation. And then R squared is 0.89, which is, it's always a percent. And this is tough for some students, it's always a percent. What that means is about 89% of the variation in the miles per gallon can be explained by the weight of the truck. That's what R squared means. It's the percent of the variation that can be explained by your predictor variable, which is weight. How much of the variation in miles per gallon can be explained by the weight of the truck. Okay, slope and Y-intercept. Slope and Y-intercept. We'll get those from Statcrunch. It has the equation is right here. The slope will be negative 0.155, and then the miles per gallon, the Y-intercept is 8.56. Yeah, sure, Nick. So the way I got these is under stat, regression stats, simple linear. That's where you do the correlation. Stat, regression, simple linear. And then you put your X variable, which in our case is the weight of the truck, and the Y variable is the miles per gallon. Yeah, no problem. So we had a slope of negative 0.155 and a Y-intercept of 8.56. You are very welcome, Emily. Negative 0.1555. Y-intercept was 8.56, I think, 8.56. 8.56, yeah. So what this means is for the slope, this means that for each additional, I think it's ton, is it each additional weight, is it ton? Yeah, each additional ton, the miles per gallon goes down by 0.155. Okay, so it's a slope and it's the change in Y over change in X. The Y-intercept is if you had, according to this, if you have a truck which weighs 0, it would get 8.56 miles per gallon. So a lot of times this is ridiculous, and you would say it may be better to stay outside of the scope of this model. And that's often the case for the Y-intercept, that a 0 for X won't make sense for that particular situation. Okay, regression equation. The miles per gallon will be, we had it 8.56 minus 0.155 times the weight. That's our equation. We're going to use that equation to predict the mileage for trucks with a weight of 15 tons. The miles per gallon will be 8.56 minus 0.155 times 15. And I'm just using Google as my calculator here. 6.235. miles per gallon. I think that's it on the regression. Are we done? I think we're done. Huh. Yeah, Sydney, good question. Let's do this same one. Now, you're going to make me enter all this data in. So you're going to have to be patient. Do you have your calculator in front of you, Sydney? Okay. So first of all, I want you to go to second and 0. There's a catalog. I want you to go to catalog. And I want you to scroll down to, we page down? Oh my gosh, my finger's going to cramp up here. I want diagnostics on. There it is, diagnostic on. And I'm just going to hit enter and say, okay, fine. So you have to do this in order to see the R and R squared. You might already have done it if you did this in class once before, so you might be fine. But you want to do that, make sure that diagnostic on. So that was under the catalog. It's the only way to get it is under the catalog, second 0, and you scroll down. Okay, now we got to enter in our data. I mean, I could tell you how to do it if you want. We don't have to do it. So it's under stat, calc, linear regression. So stat, calc, linear regression, and you put your X list and Y list, and then go down and hit calculate. Now it's not going to work for me right now because I don't have the data entered in. So I'd have to do stat edit, and under L1, I got to type in all these data again. Maybe I can do it on the keyboard really fast. And know those 2 summers of data entry are going to come into use someday. Oh yeah, nice. Oops. I can just type, nice. I don't have to click the buttons. What the heck? 12.75, go, 21.25. This would be a nice check to see, like the technologies should give us the same thing. If not, then I have made a data entry error somewhere, which is quite possible. I have a sneaky suspicion that we're missing one. Nope, there's only 7. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6. Okay, all right. So let's try this here. We've got them entered in. Okay, I'm going to quit to the home screen. So I'm going to go stat, calc, linear regression. And my X list was L1. And then the Y list was L2. We're not going to use the frequency list. That is more complicated. That's if you have like 6 trucks of the first kind and 4 trucks of the second kind and 8 trucks of the third kind, et cetera. So you're not going to do that. You're not going to do that. And we go down and hit calculate, and we get kind of all the same stuff. Hey, it worked. Right? That's all the same stuff we got. Negative 0.94, 0.89, negative 0.155, and 8.56. Yay, it worked. All right. This is a good question, Nick. This is this fine detail on regression for many faculty is something that they really hope to get to at the end of the semester. It's not an optional topic, but some people don't get to it, especially in a semester when we lose a week and we're in the middle of a global pandemic. So I wouldn't sweat it, and I would say you're probably not going to have it on your final. Or if you do, you could write a note like, we did this in the review, but I don't remember ever learning this. So that's kind of my bad answer to that question. It's quite possible that you never did learn it. It's in the course. It's supposed to be taught, but sometimes you run out of time, and then especially this semester. Emily, you only have to do that once. So once you've turned the diagnostic on, you're fine. Why is the diagnostic always not on? I don't know. I don't know. It is not always on. So, but once you turn it on, you're good. Unless you like reset your battery, like if the whole calculator gets reset, then you'd have to turn it back on again. Yeah. Yeah, no problem, Nick. Yeah, if you haven't seen any of these plots and like scatter plots and stuff, you're like, wait a minute, is this a different class? What's happening here? So yeah, it's in the class. It's supposed to be taught, but sometimes people don't get to it, or and then especially like we lost a whole week, and you know it's been crazy. So I think that's I'm sure that's just what happened. Okay, I think I answered all the questions. Sydney, we're good with the TI-84. We're good there. Okay. We missed some earlier stuff for the calculator. So if you're interested, we did confidence intervals and hypothesis testing. So if you want to, like if you watch the replay, I'm going to post this. We didn't do any calculator stuff, but they're all under the stat menu under tests. And it's t-test and 1 proportion z-test that you want. Z-test, 1 proportion z-test. Oops, sorry. So it's t-test for means and 1 proportion z-test for proportions, and then t-interval for a confidence interval for a mean, and there should be a 1 proportion z-interval confidence interval for proportions. So we can do that. We still have like a half hour left, so we could do that if no one else has any additional questions. It seemed to me, based on reading the room and the comments that were here, it seemed to me that we only had 102 people here. And that's, okay, oh, there is more stuff here. Well, there's another couple pages. Ooh, I thought we were done. So the 120 stuff is here. Did anyone who, trying to decide how to use our time here. Half hour. Maybe we should just keep going. I would like to, since I know I have at least one calculator person here, maybe go back and do some of the earlier stuff, but I think we should just keep going because we've really made good time. Only have a half hour left. So let's just keep going here. Let's just do that. For those who maybe joined us late, feel free to interrupt at any point if you have any specific questions. We have a file. I think I posted the link earlier. I can link that again. I keep pasting it in the chat. You have to copy paste into your browser. It's kind of annoying, but. Ooh, no, wait. Professor Kernler, what are you talking about? You can post files. That's so cool. Ha! There we go. That was more efficient. I just noticed there's like, oh, it says file. Right here it says, oh, you can attach a file. Okay, so let's just keep going. Finding some probabilities. Well, these are z probabilities, z greater than -1.79. I'm going to do this in Statcrunch maybe once, maybe for a couple of them, and then calculator for another one. So that's a calculator, normal calculator, and then all you do is z is mean 0 and 1, and we'll just do greater than, oh, I forgot what it was, -1.79. There's the probability. You can actually, in Statcrunch, copy this. Copy image, paste. Done. I do tell my students, like, don't just copy and paste things. Make sure you actually get the answer. So I want to make sure that you understand the answer is the 0.96 thing there. So make sure to answer the question for your class too. And let's just talk about how to do that. The rest of them are just as easy. Let's talk about how to do that on the TI calculator. Now, I haven't done this on the calculator in about 10 years. So, distribution, just that's what it is, distribution. Normal, we want CDF, we want cumulative. Lower is negative, that's the -1.79. And then upper, we basically want it to be infinity. So you can just put like a really big number. Doesn't really matter. Mean is 0, standard deviation is 1. This is a z, mean 0, standard deviation is 1. So again, that was distribution, normal CDF. Same thing, right? 0.96. So again, second distribution, normal CDF, normal CDF. And then you enter in the lower and upper limits. And if you have an upper limit that's infinity, that it goes forever, you just put like a really, really big number. If you have a lower limit that goes to infinity, you just put a really, really, really big negative number. Just put a negative sign in front of it. I guess we could do B and C. I mean, once you've done one, they're kind of all the same. Less than 1.79, so I'm just going to make this less than, or not 1.79, 1.55. See? Switch. Copy, copy, paste. I hope for those that are using the calculator, you don't like start getting mad at your instructors for not using Statcrunch. Sorry. There's a between option here. We should probably do this one on the calculator because there is not a bit, well, there is a, it's just, you got to be a little more careful. 1 to 2.65, 1 to 2.65. Okay, so that's 0.155. So on the calculator, you would do, again, normal CDF there for that one, and you would just put the lower, that one's actually a little bit easier. You don't have to do infinity. You just do the lower and upper, the 1 to 2.65. So we would do 1 to 2.65, right? Yeah, 1 to 2.65. And you see the 0.155, same thing. Same thing as Statcrunch. You don't get a different answer, it's just a different way to get there. Number 14 is actually a challenging one. This one is difficult. I think the next two, if I remember correctly, are challenging for people. Okay, so these are the distributions of the sample mean and the sample proportion. Okay, so work with me here. U.S. Census Bureau reported in 2009, 46.3% of people aged 45 to 34 had never been married. Simple random sample of 120 is conducted. It's conducted. You conduct a sample? I don't think that's the right verb for a sample. Anyway, like collected would probably be better. Sorry, these aren't my questions. I'm using someone else's stuff here. So the mean of the sample proportions. What this is saying is, okay, you have sample size of 120. Sometimes you'll get a sample proportion that is, maybe it's 40%. Other times it's 50%. Maybe it's 45%. Maybe it's 48%. And so it might vary. So the sample proportion itself is a variable, and it has a mean and standard deviation. So the mean of all of the sample proportions is actually the population proportion, which in this case is 0.463. Trying to like underline it. Okay, so the mean of all of the sample proportions is the same as the population proportion. On average, you would expect to get the same sample proportion that you get that the population proportion is. The standard deviation, though, is a little funkier. It is the square root of p times 1 minus p all over n. I don't have a quick way to explain why that is. Sorry. So this is 0.463 times 1 minus 0.463 all over 120. All right, I'm going to try to copy that. Oh, I got the approximately under the equal sign. I don't know if you have formula sheets. I hope so. It's kind of unreasonable to ask you to memorize this. Good question. Let me get back to that, Nick. 0.0455. So the proportion here, when you write proportions, you typically write them as a decimal. It's not wrong to say 46.3%. It's not wrong to say that, but usually for proportions, we usually leave them in their decimal form. So I would want you to see 0.463. That's what I would want. And this, I missed my decimal here, 0.0455. Does that answer your question? Yep. Okay, good. Right now, sketch a curve, then find the probability that more than 40% of the people in this sample have never been married. Okay, so I'm going to draw the curve in Statcrunch. We can talk about how to find this probability later in the calculator. But in Statcrunch, this is a normal probability. Calculator, normal. We have the mean. The mean is the 0.463. This is, to your point, Nick, this has to be 0.463 here. You can't write it as a percent here. Statcrunch needs it to be a decimal. Standard deviation was 0.0455. And we want to find the probability that more than 40%. Okay, find the probability of having more than 40%. So if you're drawing this by hand, you would draw a bell-shaped curve. The 0.463 is in the middle. And if you want to draw the number of standard deviations, it's 3 standard deviations pretty much to the edge. So this is about 0.05. If you multiply by 3, that's 0.15. So when you add, you get about 0.6 and 0.3. So there's that symmetry to it here. I'm just going to copy this and paste it over here. So probability of having a sample proportion of more than 0.4 is approximately 0.917. Okay? That's using this P, the original population proportion for the mean, and then using this crazy formula for the standard deviation. Last one here says, would it be unusual if more than 55% had never been married? We're going to do this the same way. We're going to do a chart again, but instead of putting 0.4, we're going to put 0.55. So we're going to put, would it be unusual if more than 55%? That's pretty unusual. Pretty unusual. I need to make some more space. Gonna like cheat and float these. Sorry to like waste time where you're watching me like format a Word document, but just trying to get some more space here. Oh, it's kind of big too. How's that? Hey, we got it on. Okay. So would it be unusual? Well, to know if something is unusual, we need to know what its probability is. So probability of getting a p hat of more than 0.55 is approximately 0.028. And since the cutoff for unusual is like 5%. This is less than 0.05, which sounds, I don't know if this sounds familiar. This sounds like the hypothesis testing we were doing at the beginning. Yeah. Since this is less than 0.05, we would say that this would be unusual. I guess I have extra space now, so no need to wrap up there. Oh, what happened to our number? So I don't know if you have any questions based on that one. In my opinion, I would label this particular type of problem like one of the peak difficulties for 102 students. I almost feel like the stuff after it is better. All right, the chat is very quiet, partly because we only have a few people here, partly because maybe you're not even sure what to ask, so that's okay. All right, what do we do? How are we doing here? 2 more? Let's do it, we can do it. Okay, next one is the other section in chapter 8, I believe. Chapter 8, this is the other section. This is about the same thing, but the distribution of the sample means. So we have daily high temperature in Chicago is normally distributed with a mean of 28 degrees Fahrenheit. So the mean is 28. Standard deviation is 9.7. A random sample of 31 days is selected. So here, the mean of the sample means is equal to the mean of the population, which is still 28. The standard deviation of the sample means, and this is a formula where I'm hoping that you have a formula sheet. Sorry. And you're able to write this down. I mean, I guess, you know, maybe your instructor is asking you to memorize that. I do not, but everybody's different. But that's a standard formula for the standard deviation of the sample means. That would be, in this case, 9.7 over the square root of 31. And we'll need a calculator for that. $1.74. Sorry. And now we're going to do our probability. Let's do these, maybe let's do these with the calculator. So I don't know. See, the problem is I can't sketch here very easily without pulling it over to my other monitor and then drawing on it. And that's kind of annoying. So maybe I'll do, see, these are all pretty much the same type of question. So let me do, gosh. Let's do A, and we'll do it in Statcrunch, and then we'll show just how to find the probability in the calculator. So it's still normal probability. Normal probability, the mean was the overall mean 28. The standard deviation, so now we're finding the probability that a sample mean would be above freezing. So it's not 9.7 for the standard deviation, it's 1.74 for the standard deviation. We want to find the probability that the mean would be above freezing, so above 32. Copy the image, paste, there we go. So about 0.01 probability. In the calculator, you have to do all these same above calculations, and it's a normal probability. So it's still the normal CDF, second variables to get the distribution. And you have normal CDF. The lower limit, what are we doing? Above freezing. So 32 is the lower limit, and like infinity is the upper limit. Our mean is 28, and our standard deviation was 1.74. And we got the same thing, 0.01, 0.011. So it's all about that normal CDF. Yeah, that's correct, Nick. That is correct. You have to, when you're finding, the key is find the probability that the sample mean, that's the key, that the sample mean would be above freezing. That tells you to use the sigma x bar. Those are the key words to look for. Because I could ask, what is the probability that a randomly selected day in December is above freezing? Well, that's one individual. And so if I were going to do that, that would be above freezing, so 32 or up, but the standard deviation would be the, was it 9.7? Because that's a question about the probability about one day. But this question is about a sample mean, and that key language there about sample mean tells you to use the 1.74. All right, so let's do the next one, find the probability that the high temperature, would be below freezing. I just did that, right? A day. Edit. Oh, wait, can't, not safe. We're gonna do 9.7, but this one it said below freezing, right? Kind of being sneaky. Oh, not 0, sorry. 0 is not freezing. I mean, it is in Celsius, but this is Fahrenheit. Okay. So here we're find the probability that the high temperature of a randomly selected day would be below freezing. So this actually exactly addresses Nick's question there. So about 0. We'll call it 66 probability. And the difference was that we used 9.7 for the standard deviation there. Would it be unusual for the high temperature of a randomly selected day to be over 40? All right. So that's this same one, because we're still looking at days. Would it be unusual to be over 40? Nope. I mean, a little rare, but doesn't meet that threshold. Let's say no, it would not be unusual because the probability is above 0.05. Well, this is mean. It keeps switching back and forth. Now it's saying find the 20th percentile of the sample mean. So now I got to go back and change the standard deviation to 1.74. And this one is different. It's asking for the 20th percentile. So that means I want the value where there is 20% less than it. So the x is the value I'm looking for, less than, and then 20% is here. See, this value, whatever this is, there's 20% less than it. That's what percentile means. So I'm going to copy that. I don't know how you all are taking exams right now, probably just in Statcrunch. I'm not. I'm having my students do this kind of work, and I'm asking them to do screenshots like this, so I know exactly how they got their answer. So 26 20th percentile is about 26.5 degrees. Oh, I could type, there we go, degrees Fahrenheit. Okay, we're down to our last question. I'm trying to keep my eye on the chat, so pop something up there if you want. This one seems a little manufactured. I remember reading this one before. 5 males with a particular genetic disorder have 1 child each. So all these 5 males have the same disorder, and they each have 1 child. The random variable x is the number of children among the 5 who inherit the genetic disorder. And so you could have anywhere from 0 to all 5. Calculate the probability that none of the children have the disorder. That would be the probability that x equals 0. So I feel like this is a letdown after the hard problems we've been doing lately. It's just given, right? 0.001. Calculate the probability that 2 or 3. What is happening? Probability of 2 or 3 would be 0.0879 plus 0.2637. And we'll just calculate that. .3516. Calculate the probability that at least one of the children will have the disorder. Okay, I have a better idea, at least one. So the way we'd have to do this, if we're going to take it literally, well, at least one means it's the probability that, I need to use my equation editor here, probability that x is greater than or equal to 1. So that's the probability that it's 1.0146 plus it's 2.0879 plus it's 3.2637. This is fine, plus it's 4.3955 plus it's 5.2373. But I would make you the argument that it would be easier to say that this is, using the complement rule, 1 minus the probability of none. And I don't even need my calculator for that. That's 1 minus 0.001, which is 0.999. So if you want to know what all these added up are, it's 0.999. And if whoever wrote this problem correctly, or whoever wrote this problem did it correctly, ding, it's like magic. It's like magic. How did he do that? So that's the complement rule. When you have a complex thing you're looking for the probability of, sometimes you can look at the opposite, the complement of it, and find the probability of that instead. Okay, find the mean and interpret in the context of this problem. So the expected value here, the way you do this is you multiply the value times its corresponding probability and then add them all up. So 0 times 0.001 plus 1 times 0.146 plus 2 times 0.0879 plus 3 times 0.2637. We bored yet? I'm dying here. 0.3955 plus 5 times 0.2373. We're going to copy that and we'll just paste that over here. 3.88. So that's the expected value. This is from a probability. If you know the outcomes of a probability experiment and you know their corresponding probabilities, this is for a random variable, you can find its expected value or its mean, and you do that by multiplying each outcome by its corresponding probability and then adding them all up. The meaning here is that if we have 5 males with this condition, on average, 3.88 of their children will have the condition. 3.88 out of 5. Well, let's word it this way. Suppose we have 5 males with this condition who all have a single child. There we go. This means that if we have 5 males with this condition who all have a single child, on average, 3.88 of the children will also have the condition. But its expected value is an average. It's a long-term average. All right, I am going to skip E and F because not really sure what F means. Don't really do this in my class, and no one calculates the standard deviation, and I apologize if that comes up. Your teacher should not ask you that because that never really comes up. And it's a crazy calculation, not really worth our time. So I apologize for that. I'm kind of tapped out here. It's been a long day. It's 2 hours. Okay, I think I'm going to call it there. Are there any last requests from any of the earlier questions or any calculator skills you've been studying? Anything additional in Statcrunch that you wanted to go over? Any last requests? Yeah, you're welcome, Nick. Yeah, Sydney, that was the R in the calculator, the correlation coefficient. So that was here, that was stat calc linear regression. And you put your data in list 1 and list 2. And then when you hit calculate, the R there is the correlation coefficient. That's the correlation coefficient right there, -0.94. That was for the example, oh, which one was that? It was like the trucks. Number 8. That's this R value here. Yeah, it's about, like a lot of this is knowing what these symbols mean too. So what is this R? You're asked about correlation coefficient, but then I asked for R. So yeah, so R is the correlation coefficient. Yep. Any other requests? Okay, I think we're going to call it there. Thanks for coming, everybody. I will send the chat here with the record of who is here so that Mrs. Walker and anybody else who's given extra credit will know that you were here. All right, I'm ending the meeting. Yeah, you're welcome, very welcome, Emily. Thanks, everybody. Take care, Nick. Bye, Sydney. Nice seeing you again. Well, not really seeing you, but nice having you here. Take care, everybody.